confidence levels hovering around.
As you peer into the endless expanse of the night sky, dotted with countless twinkling stars, a timeless question echoes in your mind. Are we truly alone in this vast universe? This enigma has puzzled humanity for millennia, igniting sparks of curiosity in astronomers, philosophers, and dreamers across generations. From ancient stargazers charting constellations to modern scientists probing the cosmos, the search for answers has continually driven us to push the boundaries of knowledge. Today, that quest takes a monumental leap forward with the launch of a revolutionary tool orbiting high above Earth, the James Webb Space Telescope, JWST. This is no ordinary observatory, but humanity's most powerful eye into the depths of space, unveiling secrets hidden for billions of years. Imagine a machine so advanced it can peer back into the universe's infancy, capturing light from the very first stars and galaxies. The JWST, with its massive golden mirror spanning over 21 feet, unfolds like a cosmic flower in space. Designed to detect infrared light that pierces through dense cosmic dust and reveals what was once invisible, it has transformed our ability to observe the universe. Launched in December 2021, the telescope now rests in a stable orbit nearly 1 million miles from Earth, far from the planet's heat and light pollution. Its instruments, cooled to near absolute zero, enable clarity that dwarfs its predecessor, the Hubble Space Telescope. Yet, what makes the JWST truly groundbreaking is its ability to scrutinize distant worlds, exoplanets orbiting stars beyond our solar system. Among these, one world shines as a beacon of possibility, K2-18b. Discovered in 2015 by NASA's Kepler Space Telescope, K2-18b orbits a dim red dwarf star named K2-8 about 120 light-years away within the star's habitable zone, where conditions might support life. K2-18b resides in the constellation Leo, an astonishing 120 light-years away. Light from this planet takes 120 years to reach us, meaning we observe it as it was when Earth was still recovering from the early 20th century. Classified as a subneptune, K2-18b is roughly twice the size of Earth and 8 times its mass, bridging the gap between rocky planets like ours and gas giants like Neptune. With no direct twin in our solar system, its nature remains deeply mysterious. Could it be a rocky core wrapped in thick layers of gas? Or perhaps a vast ocean world concealed beneath a shroud of hydrogen and helium? In 2023, the James Webb Space Telescope turned its gaze toward K2-18b, and what it revealed sent shockwaves through the scientific community. Using a method known as transmission spectroscopy, astronomers studied the planet as it transited its star. In these fleeting moments, starlight filtered through K2-18b's atmosphere, with certain wavelengths absorbed like scanning a cosmic barcode to reveal its chemical makeup. The data uncovered water vapor swirling within the skies of this distant world, a discovery of profound significance since water is the universal solvent and the cradle of biology on Earth. From the deepest ocean trenches to the highest mountain peaks, finding it on K2-18b hints at the possibility of alien oceans, cloud systems, and perhaps even rain cycles far from home. Yet, the revelations did not end there. The JWST also detected carbon dioxide and methane, gases that could point to geological activity or perhaps even biology itself. Methane, in particular, is tantalizing because it is quickly broken down by stellar radiation and must be replenished by some ongoing process. Could volcanoes be responsible, or could it be something alive? Then came the most astonishing clue: traces of dimethyl sulfide, DMS. On Earth, DMS is produced almost exclusively by marine phytoplankton, the tiny organisms that anchor the ocean's food chain. This compound is considered a biomarker, a chemical whisper of life. Its presence on K2-18b raises a stunning possibility. Could microbial life be thriving in its atmosphere or within hidden alien seas beneath the clouds? The red dwarf star that K2-18b orbits is cooler and smaller than our Sun. Yet, it flares violently, unleashing bursts of radiation that could strip away planetary atmospheres or sterilize surfaces. Remarkably, however, K2-18b appears to retain its thick envelope, perhaps shielded by a strong magnetic field or protective layers of dense clouds. What makes this planet even more compelling is its location within the star's habitable zone, the so-called Goldilocks region, where conditions allow liquid water to exist. K2-18b orbits just 0.14 astronomical units from its parent star, much closer than Mercury is to the Sun, and completes a full year in only 33 Earth days. Early estimates once suggested a 13-day orbit, but refined measurements have confirmed the 33-day figure. Despite its close orbit, the faint glow of the red dwarf balances the energy received, meaning K2-18b basks in nearly the same amount of stellar radiation as Earth does from the Sun. Climate models indicate surface temperatures might range between 0 and 40 degrees Celsius, ideal for liquid water. If K2-18b is indeed what astrophysicist Nicomedes Hahn has described as a high-end world, it could be an ocean planet blanketed by hydrogen with water composing a significant portion of its mass. Imagine a world where the surface is dominated by a supercritical fluid, something between liquid and gas, seething with exotic chemistry. Such high-end planets challenge Earth-centric notions of habitability, revealing that life-friendly environments may exist in forms and places far different from our own. Unlike Earth, where life clings to thin biospheres, high-end worlds like K2-18b could harbor vast deep oceans locked beneath immense pressure, potentially fostering life forms beyond anything we can currently imagine. Microbial colonies might drift within the upper atmosphere, or entire ecosystems could thrive in subsurface seas hidden beneath thick hydrogen layers. In fact, astrophysicist Micah Musuhan's research, published in the Astrophysical Journal Letters, suggests that such planets may actually be common across the galaxy, even outnumbering Earth-like worlds. Given that the Milky Way is filled with billions of red dwarfs, the most abundant type of star, the odds of finding life elsewhere dramatically increase. If so, K2-18b may be just the beginning, a prototype for countless habitable environments awaiting discovery. Still, skepticism remains essential in science. The detection of dimethyl sulfide, DMS, a potential biomarker, is tentative, with confidence levels hovering around 50 to 60% in early analyses. Other explanations are possible, such as sulfur released by volcanic activity or complex photochemical reactions in the atmosphere. While JWST's observations are groundbreaking, they remain constrained by distance and technology. To confirm DMS or other biosignatures, astronomers will need many more transits, perhaps dozens, stacking data to strengthen the signal. Looking ahead, missions like the Atmospheric Remote Sensing Infrared Exoplanet Large Survey Aerial, set to launch in 2029, promise sharper insights into alien atmospheres, while powerful ground-based instruments such as the extremely large telescope in Chile prepare to complement space-based efforts. The implications are profound. If K2-18b truly harbors life, our understanding of the cosmos and of ourselves will be forever transformed. Humanity would no longer stand as unique, but as part of a vast biological continuum, echoing the Copernican revolution that once displaced Earth from the center of the universe. Philosophically, this raises even deeper questions. What forms might alien life take? Would it, like us, be carbon-based or something utterly unfamiliar, shaped by exotic chemistries and environments we have yet to fathom? Could alien life be silicon-driven rather than carbon-based? And if so, how should humanity ethically approach the prospect of contact? Through listening for radio signals via SETI or by sending probes across interstellar space. The Breakthrough Listen project is already scanning K2-18 for technosignatures, artificial signals that might betray the presence of intelligent civilizations. Meanwhile, the James Webb Space Telescope has only begun its exploration. More observations of K2-18b are scheduled, with the goal of mapping its atmospheric layers and searching for additional biosignatures such as oxygen or phosphine. Phosphine, controversially reported on Venus in 2020, is produced on Earth by anaerobic bacteria, and if detected on K2-18b, could significantly strengthen the case for biological activity. JWST's NIR spec and MIR instruments are central to this effort, dissecting starlight into spectral fingerprints that reveal the molecular composition of distant worlds. Each observation is precious, as the telescope operates with a limited fuel supply for station keeping, but the potential rewards are historic. Beyond K2-18b, JWST is already revolutionizing astronomy. It has imaged protoplanetary disks around young stars, capturing the raw process of planet formation within clouds of dust. It has revealed the pillars of creation in the Eagle Nebula with unprecedented clarity, showcasing stellar nurseries where suns are born. And it has begun probing the atmospheres of other exoplanets, such as TRAPPIST-1e, a world within its star's habitable zone. The TRAPPIST-1 system, with its 7 rocky planets, may host multiple ocean worlds, though early JWST data suggests some have already lost their atmospheres, stripped away by